Here is another example problem. This has an I-beam and wedges, and we'll deal with some friction in here. So it says the I-beam is welded onto this base plate CD. So you can think of this top chunk as all one piece that's not going to separate out. And it tells us that the weight of this I-beam is 100 kilonewtons. So that's going to be acting straight down. And it's supported by a couple of wedges. So here's this wedge E at 10 degrees, and we're going to push this wedge, and that's going to raise up the I-beam. And we want to know how much we have to push this wedge up. We'll see if there's a little bit of a mechanical advantage here from this 10 degrees. And then there's one other wedge on the ground, and we're given some friction coefficients. So between the ground and the wedges and between the wedges. Let's take this apart and look at the forces acting on each piece of it. So for the I-beam, we have the wedge pushing to the right underneath it and the normal force holding it up. That friction force is 0.3 times the normal force, so 0.3 times 100 is 30. And adding these two guys together, so remember the friction and normal always occur in a pair, and you can combine those into just one resultant force. So square root of 30 squared plus 100 squared, 104.4 kilonewtons is the resultant force acting up on this I-beam. And you can get the angle that that's acting at. So remember tan theta is equal to un over n, or u, so tangent in this, the angle in this case is going to be 16.7 degrees. Equal and opposite forces going on, so the resultant force pushing up on the I-beam is also pushing down on the wedge. So that same 100 force pushing up is now going down, and we have that 30 kilonewton friction force. It's now pointing to the right on that wedge. Zooming in on this, so for the wedge, and think about which direction that friction is going in, it's resisting motion. So we're trying to push the wedge to the right, and the friction is resisting that motion and pushing back to the left. And that's happening both on the top and the bottom. So friction is fighting it on both sides. And we're also going to have a normal force underneath. So let's add that friction and normal together into the resultant that's acting underneath this wedge. So we have, we'll call that R1 and R2 on the top and the bottom of this wedge. And this is the same friction coefficient. So we know that the angle between the normal force and the resultant is 16. Let me try and redraw this. When you have really teeny angles, sometimes it's hard to keep things straight. So remember, this wedge was happening at 10 degrees. And so if you want the position of that resultant with respect to the vertical, that's going to be 16.7 plus 10. So 26.7 if you want to measure the resultant all the way to the vertical. Okay, so what we have here is three forces that are acting on the wedge. We're pushing on it, and then the top and the bottom are also pushing on it. And the easiest way to figure all of these forces out is to add them head to tail, head to tail. So let's make a giant triangle out of these three forces. So we have the resultant on the top at that 16.7 degrees, so 73.3 would be the other side of that 90-degree angle. And then we have this resultant on the bottom, trying to figure out that angle. So remember, we've got that extra 10 degrees in there. And so instead of 73.3, you lose 10 degrees. So that's going to be 26.7 on one side and 63.3 on the other side. Getting the angles figured out for these things is going to be the hardest piece of it. But once you have three sides of that triangle, and we know what R1 was, we figured out what R1 was from that top piece. So you can just use the law of sines. So That force P is adjacent to the 43 degrees, R1 is adjacent to 63, R2 is adjacent to 73, and now we have all of the sides for that triangle. And I think adding this head to tail and looking at the vectors is easier than breaking it into x, y, z components, but either way, we can solve for all the forces acting on that wedge. Putting in the last forces here, so for Q is going to be that 30 pushing against it, and then our force P was 80, so you can think about the mechanical advantage there. So you can push that wedge with 80 kilonewtons and lift 100 kilonewtons. So that's the advantage of that wedge. The friction takes away some of that mechanical advantage, takes away a lot of it. Okay, is this thing sliding across the floor? That's the last question to ask ourselves. If I take this force pushing up on wedge E, and we have an equal and opposite force pushing down on that lower wedge F, if you draw in the line of action of this force, so wedge F only has two forces acting on it, the force from E and from the ground. And those guys are going to have to be along the same line of action if they're going to cancel out and be equal and opposite to one another. So think through the angles again. On top, we have the 0.3 friction coefficient, and underneath, we have a 0.6 friction coefficient. So look at those angles. We've got 16.7 plus 10 versus 31, so we're good. We're not going to slide here. Okay, hope that wasn't too painful. Draw large pictures with these things.